Good morning, viewers. We are back again with another exciting edition of the physics lesson. We are today going to talk about a very common topic in physics, that is motion. And I hope we are going to have an interesting time together. Um, motion. Motion is something that everybody understands. We are just going to try to move as quickly into the areas that I consider gray areas for students. Anytime an object changes position with uh, relation to time, we'll say that the object is moving. Anytime an object changes position with respect to time, we'll say that the object is moving. So an object is observing motion anytime there's a change in motion, anytime there's a change in its position. If I leave where I am now and I move to another point of this class, then I am on motion. Of course, I've covered a particular distance and I've done that within a time. So generally, anytime you are on motion, your distance changes because you have to leave a particular point and you move to another. And that must be done within an instant of time. So that means for motion, for an object to move, there must be a change in position with reference to time. Now, generally, there are four types of motion. We have what we call translational motion. We have what we call rotational motion. We have what is called oscillatory motion. And lastly, we have random motion. So translational motion involves the movement of the whole body from one point to another. It involves the movement of the whole body from one point to another. Anytime you take the whole of your body and you move to another position, then we'll say that you are observing translational motion. Under rotational motion is the movement of a body around a fixed point. When you have a fixed point and an object moves around that point, they will say that the object is observing rotational motion. It doesn't have to be circular because most of the time we feel like rotational motion has to be circular motion. No, an object can observe rotational motion such that the orbit, the path is taken around that point is not circular. It could be, there are so many other um, conic sections that also look like circle. For example, it could be elliptical. It could go around in an elliptical orbit. We are going to try to touch on that later. Oscillatory motion, the to and fro motion about a point. The to and fro motion about a point. If you have a point and you have an object that is moving around that point, an object is describing its motion around two fixed points, they will say that the object is observing oscillatory motion. Random motion is a type of motion that does not have specific pattern, does not have any specific pattern. It is not descriptive. It is not predictive. We cannot say that because the object is at a particular position, this is where it will be the next moment. No. Once the motion of an object cannot be described, can follow any pattern that is not specific, then we'll say that the object is moving in a random motion. And there are so many examples of objects that observe this type of motion. When a car is moving on a straight line, it is observing translational motion because the whole of the part of the car will have to move with it. Rotational motion, the blades of your fan are moving around a circular point, which is the center of that fan. I would say that the object is observing rotational motion. For oscillatory, we all know the famed simple pendulum. When the simple pendulum oscillates about a fixed point, oscillate about two fixed points, we say that it is observing oscillatory motion. And random, the motion of gases is usually described as random. The motion of smoke particle is also usually described as random. There are so many other. Generally, uh, objects do not have only one type of motion. They do not have only one type of motion. Most of the time, they combine two or three other motions with whatever they are doing, particularly translational and rotational. When we consider the motion of the wheel of a motor car, while the wheel is rotating, So we say that it is observing rotational motion. It is also moving the car forward. It is leaving a particular point and it is going to another point. So it is also having element of translational motion. So the object, the wheel of a car, for example, is observing translational motion and rotational motion. That is what differentiates the motion of the wheel of a car or the wheel of a moving car from that of a fan. While the fan is rotating and is staying at a fixed point, so it's having only rotational, the wheel of a car is rotating and is moving the car forward. So it's having both rotational and translational, because anytime the object leaves a point and goes to a new point, then translational is involved. Anytime the object is going around a fixed point, rotational is involved. So these are the types of motion that we have. So for now, we are going to try to consider the and a very good example of translational motion that we usually refer to as linear motion. When an object moves in a straight line, we say that it is observing linear motion. And there are so many things that we can use to describe the motion of an object on a straight line. There are parameters that we can use to describe the motion of an object on a straight line. If I move on a straight line, I must have left a particular point to settle at another point. So there must be a distance between the two of them. That distance is usually represented as S in physics. It is the distance, or it is more commonly referred to as displacement, either of the two. Distance and displacement can be used interchangeably under this aspect. The major difference between distance and displacement can be seen under scalars and vector. While displacement is a vector quantity, distance is a scalar quantity. In fact, displacement, when you attach direction to distance, it becomes displacement. So displacement is the distance traveled in a specific direction. So while displacement is a vector quantity, distance is a scalar quantity. When you're solving a question where direction is really not important, then both of them are used interchangeably, and that is what we might be seeing under linear motion. They are measured in meters, kilometers, and there can be other units that we can use to represent them, but most commonly, these are the two units that we always use to represent them. Of course, if I'm going to cover a particular distance, I must have done that within a particular time. So the time is represented with T, time. Usually time is expressed in seconds, but it can also be expressed in hours. It can be expressed in minutes. There are so many other units that we can use for time, but these are the two most commonly used units that we always have. So anytime an object is moving, it must have these two. It must cover a particular distance and it must do so within a particular time. So when we have those two, then there's the need for a third quantity. That is your speed or your velocity. That is your speed or your velocity. Your speed or your velocity will help us to understand how fast are you covering the distance. If I am moving, I can take a whole hour to move between 2 points. A faster person can take few minutes to just move between the same points. In fact, speed is the major difference. Speed is what we are testing. Usually when athletes run 100 meters, sprint races, even middle distance races or marathon, they are all covering the same distances, but they are not doing so within the same time. So the speed help us to understand who will arrive there first and who will be the last place person. Of course, if you have to finish first, it means you must cover that distance within a short period of time. And if you are going to come last, it means you are going to cover that same distance within some time that is a little bit going to be more than that of the first place person. So speed will be defined as the rate of change of distance with time. Speed will be defined as the rate of change of distance with time. Speed is the rate at which you are changing your distance. Of course, if I'm moving, I'm changing my distance. The rate at which I am changing my distance, how fast am I changing that distance, is what I understand as speed. So more commonly, speed is determined by just dividing the distance that you have covered by the time that it's going to take you to cover that distance. So we do distance all over time for speed. Speed is usually represented with letter U. but there can be other letters that we use to represent it. I'm going to introduce you to that later. So I can say that the speed is your distance all over time. The speed that you have taken, the speed that you have is the distance that you have covered all over the time that it took you to cover that distance. If, for example, you have covered a distance of 100 meters within 10 seconds, that is about the time it will take some athletes to cover that same distance. It means your speed must be equal to 10 meters per seconds. Meters per second simply means meters divided by seconds, and that is our speed. So what this is telling us is for you to have covered a distance of 100 meters in 10 seconds, you must have been moving such that you will always have to cover a distance of 10 meters every second. In every 1 second, you must be covering 10 meters. That is why you'll be able to cover 20 meters in 2 seconds, 30 meters in 3 seconds, 40 meters in 5 seconds, 60 meters in 6 seconds, 70 meters in 7 seconds, 80 meters in 8 seconds, 90 meters in 9 seconds, and 100 meters in 10 seconds. So your speed describes what you will be able to do, what you have been able to do in 1 second for you to have been able to cover that distance and time. The fastest known thing to man is light. Light travels with a speed of 300 million meters per second. 300 million meters per second. That means if you give light 1 second, that same 1 second, it will cover a distance that is equal to 300 million meters, which is a great distance. If you compare that with that of an average athlete, you will understand how fast or slow the man is when you compare an average man to that of light, an average man's speed to that of light. So that is speed. Speed helps us to understand the rate at which you are covering your distance. And more commonly, speed can also be represented with velocity, can also be referred to as velocity under motion. The velocity is the rate of change of displacement with time, the rate of change of displacement with time. So remember that I said that under motion, distance and displacement are almost about the same thing. The only difference between them is that while one is scalar, the other is vector. So the difference between distance and displacement is also the difference between speed and velocity. While speed is a scalar quantity, velocity is a vector quantity. So when you attach direction to distance, it becomes displacement. When you attach direction to speed, it also becomes velocity. If I travel 5 meters to walk to school every day, then that is distance. If I have to walk 5 meters eastward to get to school every morning, then that is displacement. The eastward represents the direction in which I am moving at 5 meters. So the same thing for speed. Most of the time when we have 5 meters per second, you are probably referring to the speed. But if I attach direction to that, 5 meters per second eastward, westward, then it becomes velocity. That is why in most cases where direction is not important, speed and velocity are used interchangeably. One can be taken for the other. So the velocity is also going to have the same unit as speed. The unit of our displacement is meters. The unit of our time is seconds. So if we do that, we'll have meters. If we divide the two, we'll have meters per second. Just as I have said earlier that the unit of speed is also meters divided by seconds, which we represent as meters per second. Meanwhile, they can also be represented as kilometers. I can choose to represent my distance as kilometers and my time, I can choose to measure it in hours. So if we divide that, we should have kilometers per hour. If we divide these two, we should also have kilometers per hour. So that is all that is there to learn about speed for now. We'll move on to acceleration, another quantity that we can use to describe the motion of an object on a straight line. Now, we have talked about distance, we have talked about time, we have talked about speed. When does an object accelerate? It is possible that in trying to move between 2 points, I will choose to start very slowly. And probably as time goes by, I will now try to increase my speed. I'll try to walk faster. Particularly whenever you want to drive a car, you start from a point where the car will have to steadily increase its velocity. You start slowly, then you gain speed with time. Anytime the speed or velocity with which you are traveling, anytime the speed or the velocity with which you are traveling changes, then you are accelerating. Acceleration, therefore, is involved for bodies whose velocity or speed is changing. Therefore, we say that acceleration is the rate of change of velocity with time. Acceleration is the rate of change of velocity with time. Anytime your velocity changes, then you are moving with an acceleration. That is why generally it is not compulsory for a moving object to have an acceleration. Acceleration becomes only important when the velocity or the speed changes. When your velocity or speed is constant, the acceleration is zero. You don't have any acceleration. And there are so many objects that moves with zero acceleration. I was talking about light the other time. At any time you trap light is always going to be moving with a speed of 300 million meters per second. That means light does not accelerate despite the fact that it is moving very fast. And there are several very slow objects that accelerate. You only accelerate when your speed is changing, when your velocity is changing. If, for example, I start with a velocity of 0.1 meters per second. Of course, when you compare this with the value that I wrote for the speed of light, you say that this is almost negligible. Now, if within the next moment, you are able to increase your speed to 0.2, then 0.3 meters per second, then 0.4 meters per second. If this is the profile of your movement, such that at one point your speed was 0.1 meters per second, then at the next point you increase it by 0.1, so it becomes 0.2, 0.3, 0.4. In a layman's word, you are still moving very slow, but you are accelerating. Why? Because your velocity is changing. Anytime your velocity changes, anytime your speed changes, then acceleration is involved with your motion. Anytime your velocity is constant, no matter how high the velocity is, if it is constant, then you are not accelerating. You only have an acceleration when your velocity changes. So therefore, I'm going to define acceleration. Apart from acceleration helping us to understand that velocity is changing, acceleration also helps us to understand how that velocity is changing with time. So therefore, acceleration is the rate at which you are changing your velocity with time. Acceleration is the rate of change of velocity with time. Acceleration is the rate of change of velocity with time. So therefore, anytime acceleration is involved, I just define acceleration as the rate. When you say rate, you are dividing by time. The rate of change of velocity with time. The change in velocity all over time. That is what acceleration represents. Acceleration helps us to understand how you are changing your velocity. Now that we have said that you are changing your velocity with time, how are you changing it with time? For example, the last motion of the object that I profiled, you can see that if after 1 second, the object is moving with a speed of 0.1, by the second, the object starts moving with 0.2. By the third second, it's moving with 0.3. By the fourth second, it's moving with 0.4. Then it clearly shows that for every 1 second increase in the time, the velocity of that object is changing by 0.1 meters per second. The velocity of that object is changing by 0.1 meters per second. The velocity of that object is changing by 0.1 meters per second. That means if I give it additional 1 second, its velocity should become 0.5. If I give it 1 more second, it should be 0.6. Therefore, I can easily say that the acceleration is the change in the velocity. The change in the velocity here is 0.1 meters per second every 1 second. So the acceleration, therefore, will be expressed as 0.1 meters per second. Meters per second then per second. If we bring that together, we should have 0.1 meters per second squared because we have 2 per second here. So this is the acceleration. The unit of acceleration from what I've just done will therefore be the unit of our velocity, meters per second, all over the unit of our time, which is also second. So if we bring that together, we should have meters per second. That will be meters per second squared. That's the unit of acceleration. And where your velocity is expressed as kilometers per hour, please understand that the unit of time is also going to be hours. So the unit of acceleration will therefore be kilometers per hour per another hour. This per hour, the first one, and dividing by hour means also per hour. And I can bring that together as kilometers per hour squared. And that is the unit of our acceleration. So now that we know the 4 aspects, the parameters that we are going to use to describe our motion, starting from distance to time to speed to acceleration, I wish to represent them more appropriately with the letter that is generally used in most textbooks to represent them. Our distance is s. I mentioned that before. So don't confuse s with the speed. It's not the speed. S is the distance. In some other textbook, it might be referred to as x, but it is more commonly referred to as s. So that is your distance. Our time is t. Our velocity, I said, is u, and then our acceleration is a. The only thing now is anytime there's an acceleration, I said your velocity will have to change from one value to another value. The velocity must change from one value to another value within the time that you are considering. So therefore, it is natural for the velocity to now take up more values if there is an acceleration. If there is no acceleration, we are going to be talking about only one velocity. For example, when I talked about light, the speed of light at any time is going to be 300 million meters per second. 300 million meters per second. 300 million meters per second, as long as refraction is not happening to it. We'll discuss that under waves later. But for now, so the speed of light is always 300 million meters per second. That is just the value. I will represent it with u. But when acceleration comes into play, I'm going to have different values for my speed or for my velocity, because now for an acceleration, I said that the velocity or the speed must change. So anytime there's an acceleration, there will be a speed with which you are starting the motion. And there will definitely be another speed or velocity with which you are ending the motion. The reason why I'm using speed and velocity interchangeably here is I established earlier that when directions are not important, then both of them can be used together. So anytime I refer to speed, please, I also mean velocity. Acceleration is the change in the rate of change of the speed. That means, let us take an example of an object, like the one I told you earlier. By 1 second, let's assume that the object was starting with a velocity of 0. At the start of the motion, the velocity was 0. Velocity, I'm going to be writing the velocity here, and I'm going to be writing the time here. After 1 second, the velocity became 0.1. After 2 seconds, the velocity became 0.2. After 3 seconds, the velocity is 0.3. After 4 seconds, the velocity becomes 0.4. After 5 seconds, the velocity becomes 0.5. These are values in meters per second, that's the unit of velocity. These are values in seconds, that's the unit of our time. Now, we'll check the board. The velocity actually started with a value of 0. And after 5 seconds, the velocity became 0.5. So with that, if this is just the motion of the object, there must be letter that I'm going to use to represent this velocity, and there must also be a letter that I'm going to use to represent this velocity. And more commonly in physics, we refer to the starting velocity as your initial velocity. We refer to your ending velocity as your final velocity. So your starting velocity in this case is u, is represented with u, which was a letter I gave you for the speed or velocity earlier. Your final velocity will be represented with v, which is the velocity I gave you for the final, which I'm just writing now as your final velocity. So anytime there's an acceleration, what acceleration will cause is that it's going to give you an initial velocity that is different from your final velocity. And because they both have two different values, that is why we have chosen two different letters to represent them. So your u is your starting velocity or your initial velocity, while your v is the ending velocity or the final velocity. In a situation where the object is moving with the same velocity, in that case, it is not accelerating. If after 1 second, the object is starting from, let's assume that the object is starting from a velocity of 0.1. Then after 1 second, it becomes 0.1. It stays at 0.1. After 2 seconds, it stays at 0.1. After 3 seconds, it stays at 0.1. After 4 seconds, it stays at 0.1. After 5 seconds, it stays at 0.1. Then we can clearly see that your starting velocity, your ending velocity, and any other velocity that you are able to pick within the motion of the object remains the same. If that is the case, we said there is no acceleration. For you to have an acceleration, your speed or your velocity must change. The velocity here will remain constant. So there is no need for me to use u to represent the initial and v to represent the final. I can do that, but it is not necessary because it is just a single velocity all through. So I can represent them with u, 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 u. Or I can represent all of them with v, 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 v. V and u becomes appropriate only when we have an acceleration and when the acceleration is changed. Only when we have an acceleration and that acceleration definitely causes a change in the velocity of that object. So clearly, what acceleration will do is that it's going to give us an initial value of our velocity and a final value of our velocity, and both of them will not be equal because the velocity is changing. When something changes, it means what you are starting with and what you are going to end with will not be the same thing. So we have the initial velocity with the starting velocity, and we have the final velocity with your ending velocity. That will help us to understand that velocity sometimes can be represented with two letters, u and v. Our u is the initial velocity, and our v is the final velocity whenever there's an acceleration. Now, that said, let us try to look at the different forms of motion that we can have for linear motion. An object can decide to move with uniform velocity. And an object can also decide to move with uniform acceleration. So if these are possible, the opposite is also possible. Uniform velocity is the velocity that an object will have if its acceleration is not changing. It is the velocity that an object will have if the acceleration is zero. Sorry. If the acceleration of an object is zero, then it's going to move with uniform velocity. In that case, it means at any time, its velocity will remain the same. At any time, its velocity will remain the same. When that happens, it means that the object will be covering equal displacement in equal time, no matter how small the time may be. For example, if at any time the motion, an object decides to move with 10 meters per second, such that at any time you track the motion of this object, this is the same velocity that it's going to have. After 1 second, it's having 10 meters per second. After 2 seconds, it's having 10 meters per second. After 3 seconds, it's moving with 10 meters per second. After 4 seconds, it's moving with 10 meters per second. After 5 seconds, it's moving with 10 meters per second. So it is moving with constant velocity at all times. Then we say that the velocity is uniform. In this situation, what the object will be doing is it will be covering 10 meters every second. It will cover a distance of 10 meters every second. For every 1 second that it has, it's covering a distance of 10 meters. So it's going to be covering equal displacement or equal distance in equal time. It is not moving faster. It is not at any time moving slower. If that is the case, it means that object is going to be covering equal displacement in equal time. So when you are asked to define uniform velocity, it is more appropriately referred to as the velocity of an object that covers equal displacement in equal time interval, no matter how small the time may be. It covers equal displacement in equal time interval, no matter how small the time may be. In this case that we have used for our illustration, for every 1 second that you give to that object, it will cover a distance of 10 meters. For every 1 second, it will cover a distance or displacement of 10 meters. For every 1 second, it will cover a distance or displacement of 10 meters. So it is covering equal displacement, 10 meters, in equal time interval, 1 second, for no matter how small the time may be. What about, so therefore, if an object is not moving with uniform velocity, then it is definitely moving with non-uniform velocity. And when the velocity is not uniform, there is definitely an acceleration. There will not be an acceleration, or the acceleration will be zero when the body is moving with uniform velocity, because acceleration has to do with change in velocity. And once the velocity is uniform, it is not changing. And once it is not changing, it means that the acceleration is equal to zero. Now, what does it mean for an object to move with uniform acceleration? For an object to move with uniform acceleration, it means that since we have established acceleration as the rate of change of velocity with time, acceleration is the rate of change of velocity with time. It means that the object is changing that velocity. The object is changing that velocity with equal interval, within an equal interval of time. Is changing the velocity by equal amounts in equal time intervals. I will want to describe that with an illustration. Let us say that the motion of 3 different objects were tracked, and we observe that at this time values, the velocity of that object is taking these values. At first, it's having a velocity of 10 meters per second. It's starting from a velocity of 10 meters per second. Then, after 1 second, it's moving with 10 meters per second. After 2 seconds, 10 meters per second. After 3 seconds, 10 meters per second. After 4 seconds, 10 meters per second. After 5 seconds, 10 meters per second. After 6 seconds, 10 meters per second. Now, the motion, let us refer to this as object A. Now, for object B, the velocity of object B was tracked to be 10 meters per second. It was starting from 10 meters per second, then it became 15 meters per second, then 20 meters per second, then 25 meters per second, then 30 meters per second, then 35 meters per second, then 40 meters per second. If that is the case for B, now let us check for C. For C, the velocity of C was tracked to be 10 meters, to also start from 10 meters per second. After 1 second, it became 12 meters per second. After 2 seconds, you must have been expecting 14, but I'll surprise you a little. It is now 20 meters per second. Then it became 50 meters per second. Then it became 52 or 57 meters per second. Then it became 89 meters per second. Then it became 117 meters per second. That is the motion of this object. The question now is, how do we describe the motion of each of these objects, A, B, C? A is moving with constant velocity. It's moving with uniform velocity. The velocity from the start to the end remains the same. So the A is moving with uniform velocity. What about B? B is not moving with uniform velocity. Its velocity is changing. And when we study the change in velocity, we will discover that the velocity is changing by equal amount. From 10 to 15, it changed by 5. Then from 15 to 20, it's also changing by 5. 20 to 25, 5. When you add 5 to 25, you have 30. 30 to 35, 5 also. 35 to 40, 5. Such that you can even predict what might be the next. That should be 45 if it continues with that same motion. Now, when an object moves like this, it is increasing its velocity by equal amounts in equal time interval. They will say that that object is moving with uniform acceleration. Since acceleration is the rate of increase in velocity with time. Now, I can say that while the velocity is increasing with 5 meters per second every 1 second, I can say that the acceleration is changing. How is it changing? How is the velocity changing? It's changing by 5 meters per second. What's the time through which this change in velocity is being observed? Every 1 second. So the acceleration must be 5 meters per second. And the acceleration will be 5 meters per second squared. So the acceleration of the object is 5 meters per second squared. And it is changing at 5 meters per second by 5 meters per second by 5 meters per second by 5 meters per second. When an object moves like this, it's moving with uniform acceleration. That is why we define uniform acceleration as the acceleration of an object that moves such that it increases its velocity by equal amounts in equal time interval. I hope you note that it is the displacement that we use to describe velocity. It is also velocity that we use to describe acceleration. Because once you have a change in displacement, velocity, you have velocity. Once you have a change in velocity, you have an acceleration. So as the displacement is changing by equal amounts in equal time interval, you are moving with uniform velocity. If your velocity is changing by equal amounts in equal time interval, then you are moving with uniform acceleration. Now, let's check the motion of C. C is also accelerating. Yes, because its velocity is changing. The first time it changed by 2 meters per second, then it changed by 8 meters per second. Then it changed by 30 meters per second. Then it changed by 7 meters per second. Then it changed by 32 meters per second. Then it leaped by 28 meters per second. So while the velocity is changing, suggesting that there's an acceleration, the acceleration is not the same. The acceleration here is 2 meters per second squared because it changed by 2 meters per second within the first second. The acceleration here is 8 meters per second because 8 meters per second squared because it changed by 8 meters per second in the next second. So when the change in velocity is erratic, when the change in velocity is random, when the change in velocity is such that it does not follow any specific pattern, it is not the same. The change in that velocity is not the same as we have for body B. Then we say, yes, it's accelerating, but it is accelerating non-uniformly. So for the first motion is moving with uniform velocity. B is moving with uniform acceleration. C is moving with non-uniform acceleration. And I hope we understand those concepts. We can now move on to the equations of motion. When an object moves, there are certain equations that governs its motion, particularly when it moves with an acceleration. Anytime an object moves with an acceleration, there are certain equations that help us to describe the motion of that object. Now, I'm going to start with the equation of motion. I'm going to start with the definition of acceleration. We said acceleration is the change in velocity with time. It's the rate of change of velocity with time. It's the rate of change of velocity with time. Now, I just told you that if the velocity is going to change, it will change from an initial value that we have referred to as u, and it will change to a final value that we are referring to as v. So if that is the case, if the initial velocity is v, and the final velocity is, if the initial velocity is u and the final velocity is v, the change in velocity must be equal to v minus u. So the rate of change in the velocity, when we mention rate in physics, it means divided by time. The rate of change in velocity will be equal to, is referred to as all over t. The rate of change in velocity will be v minus u, which is the change in the velocity, divided by t. So when I write acceleration like this, it means the change in velocity all over time, which is also referred to as the rate of change of velocity. I can now work on this equation by bringing t here. What I have written is the mathematical representation of the definition of acceleration. Acceleration is the rate of velocity, rate of change in velocity with time. So I have v minus u is equal to at. So then v must be equal to u plus at. And that is our first equation of motion. So anytime we need the final velocity, it is the initial velocity plus the acceleration multiplied by the time. So that should give us the first equation of motion outrightly. So then we can continue from there. If an object is having a distance, the velocity of that object, I had earlier said that the velocity is distance all over time. The velocity of an object is distance all over time. The velocity, therefore, the distance, therefore, must be equal to, if I cross multiply, velocity multiplied by time. But this equation is only true if the object is not accelerating, because it is only when the object is not accelerating that we can just refer to the velocity as u. When acceleration is involved, the velocity must be, there will be an initial velocity and there will be a final velocity. Particularly when the uniform acceleration is involved, there will be an initial velocity and there will be a final velocity that the object's velocity has changed to. So if I am now going to find the distance where I have the initial and the final velocity, it cannot just be expressed as this. I have to now find, if you ask me what is the velocity that I will now use, since there's an initial velocity and there's a final velocity, I will just assume that I will use as my velocity the average of the two velocities, the average of the initial and the final velocity. An average is the two items added together divided by 2 multiplied by the time. So it is still this equation that I've been able to rewrite in this form. Mind you, this is only also correct when the object is moving with uniform acceleration. This is correct when the object is moving with uniform velocity, such that there is no final and there is no initial velocity. Both can be represented as u. But where there is a final and an initial velocity under uniform acceleration, then we can find the average speed or the average velocity and multiply it by time to get the distance. With these two equations, I can now find more equations to work with. For example, if I make my v the subject of the formula, is already the subject of the formula here, and I decide to put it inside this expression, if I substitute for v inside equation 2, I should be able to revert the equation into another equation of motion. For example, equation 2 is s is equal to u plus v all over 2 multiplied by t. If that is the case, I can now substitute for my v in this equation. If I do that, I will have s is equal to u plus, instead of v, I'll put u plus at multiplied by t. Remember that we still have it divided by 2 here. So if I continue, I will have s is equal to 2u plus at multiplied by t divided by 2. So that becomes s is equal to, if I open this bracket, I will have 2ut at squared all over 2. If I decide to split it, I will have 2ut all over 2 plus at squared all over 2. 2 can cancel out 2. I will have s is equal to ut plus, I can rewrite this as, if you are dividing by 2, is the same with multiplying by half at squared. So this gives me another equation of motion that I can also use. Let me call this equation 3. Equation 3. And there's still more that I can get. If I decide to, here I've substituted for V, if I decide to substitute for T, I should be able to get another equation of motion that I can use for the problem. Now let us try to look into that. If I make my T the subject of the formula in the first equation, and I still substitute it into the second equation, I should be left with another equation. I have V is equal to U plus AT. If that is the case, then I can bring U to the other side. It becomes V minus U is equal to AT. If I divide both sides by A, then I'll get an equation in which T has been made the subject of the formula V minus U all over A. If that is the case, then I can easily substitute for T. So my S should therefore become V plus U all over 2 multiplied by my T. I've already made my T the subject of the formula. I can substitute for it, V minus U all over A. So I can decide to multiply my numerators and my denominator. I will have V plus U, then V minus U all over 2A. If that is done, I can say that S is equal to, you can break this bracket by using V to multiply both items in the other bracket, and by using U to multiply both items in the other bracket. V times V is V squared plus V times U is UV. Okay, is V times minus U is minus UV plus V times U is UV minus U times U is U squared all over 2A. If we cross multiply, we should have 2AS is equal to V squared. From mathematics, I hope we know that minus UV plus UV can cancel out, minus U squared. So I can bring U squared to the other side such that I will have V squared is equal to U squared plus 2AS, which will give me another equation of motion. I'll call this one equation 4. So we have the first equation, V is equal to U plus AT. We have the second equation, X is equal to V plus U all over T. We have the third equation, X is equal to UT plus half AT squared. And we have the fourth equation, V squared is equal to U squared plus 2AS. These are the 4 equations of motion. You don't have to learn it in order. You can learn it in any other. For example, you can call this one the second equation, call this one the third equation. What is more important is that you know the equation. It is not necessary that you know the equation in the order in which I've written them on the board. So we'll now move on to how we can apply those equations. For a quick recap, I wish to list out the equation that we have derived thus far. We have V is equal to U plus AT, S is equal to U plus V all over 2 multiplied by T, S is equal to UT plus half AT squared, and V squared is equal to U squared plus 2AS. It is easy to use all of these equations, very easy to use all of these equations. Why? I want you to observe that each of these equations has 4 items. There are 5 things that we have talked about, so far. We have initial velocity, final velocity, acceleration, distance, and time. Each of these equations has 4 of these 5. For example, the first equation has V, U, A, and T. It does not have S. The second equation has S, U, V, T. It does not have A, acceleration. The third equation has S, U, T, and A. It does not have V. The last equation has V, U, A, and S. It does not have T. That means to solve a motion problem, you will have to be working around, to solve using any of these equations, you have to be working around 4 parameters. 4 parameters. And what I would advise students to do is, in solving a motion problem, the question will naturally give you 3 things. The question will naturally give you 3 things, and will ask you to find one. Anytime you are solving a motion problem, the question will give you 3 parameters and will expect you to find one. If that is the case, you now have to look for which equation has those 4 that your problem requires. The 3 that you have been given and the one that the question wants you to find. If, for example, the question has given me VAT and wants me to find U, I can easily use the first equation. I have to use the first equation. If I've been given SUT and I want to find A, obviously it is the third equation that I'm going to use. That's the one that has those 4. If I've been given A, S, and U, and you want me to find V, then it has to be the third equation. So you have to look for the equation that has the 3 items that you have been given and the one that you are looking for. That is how to approach this equation. There's only one quantity of these 5 that is in all of this equation, and that is initial velocity. There's an initial velocity in each and every one of those equations. That means it is almost impossible. It is not possible to solve a motion problem without the initial velocity. It's either you are given initial velocity or the question directly wants you to find it. You cannot solve a motion problem without either giving the initial velocity or required to find the initial velocity. Now we are going to take 1 or 2 examples to see how this can be done. But before then, there are terms that are used to give you some items that will not require that they use those items, they give you those items directly in physics. And those are the things you must be watching out for. This word, rest, is very, very important when you are solving a motion problem. Anytime you are told that an object is at rest or an object is at rest, it means that the object is in a state where it is not moving. For example, if I choose to stand, then I am at rest. If you choose to sit, you are at rest. When you put your chair or your items anywhere, those items are at rest. When an object is at rest, it is not moving. When an object is not moving, both its distance and at that point, its velocity is equal to 0 because it's not covering any distance at that point. It can now decide to move away from rest, but while at rest, its distance is 0, but most specifically, its velocity is 0. Most specifically, its velocity is 0 because you are not moving. It is only when you move that you have a velocity. It is only when you move that you can have speed. When you are not moving, you are not having speed, you are not having velocity. So now that we know that an object is at rest, when an object is at rest, it means that the velocity is 0. It doesn't mean that an object at rest will have to continuously always be at rest. No. It is possible that in starting a motion, I choose to start from rest. If I choose to start from rest, it means at the time my velocity was 0. Now, if I decide to now move from that position of rest, I am now moving to a state where my velocity will change, where my speed will change. So most times, objects start from rest, but they now gradually build their velocity. And once that is done, there's an acceleration because you are starting from a point where your velocity is 0 to another point where your velocity is not 0. And anytime you change your velocity, mind you, you now have an acceleration. So if you are told that an object is coming from rest, and an object is coming from rest, from has to do with your initial position of motion. From rest, now that we know that rest means velocity is equal to 0, anytime you are moving from rest, please note that your initial velocity is 0. You are starting from a point where your velocity is 0. It is also possible that while moving, you now choose to approach a point of rest. For example, if you are going to park a car, the car was moving before. In trying to park it, it is now coming to rest. When an object is coming to rest, I told you that rest means that the velocity is 0. To is helping us to understand your final point, your final position of motion. It means your final velocity must be equal to 0. Please watch out for these words when you are solving a motion problem. Anytime an object is coming from rest, it means that the initial velocity is 0. You have been given the initial velocity. You just need to write it out. Anytime an object is coming to rest, the final velocity must be 0. It is not possible when there's an acceleration, a single acceleration, for your initial and final velocity to be 0. It is only one that can be 0. It's either your initial is 0, because when you're having an acceleration, both the velocity initial and velocity final cannot take the same value. So, and there are so many other words that they can use instead of rest. You can be told that the object is brought to a halt. The object is brought to a stop. It still all means the same thing. Stop, halt, rest. They are all referring to a point where the velocity is equal to 0. We can also be told that the object is moving with uniform velocity. There are so many other words that means the same thing with uniform that can also be used. You can say that the object is moving with a steady velocity. You can be told that the object is moving with a constant velocity. We can also be told that the object maintained its velocity. It maintained its velocity or speed. When that is done, it clearly means that the object is, all of these words are directly telling you that the velocity is not changing. It's not changing. And anytime the velocity is not changing, there's no acceleration. Or more appropriately, you can say that the acceleration is 0. When something does not exist, or when something does not have a value, we can give it a value of 0. So please always watch out for this item anytime you are solving a motion problem. And we are now going to take one or two examples to see how they can be used in a motion problem. The very first example we are going to take here is one: a body accelerates uniformly from rest at 3 meters per second squared. Its velocity after traveling a distance of 24 meters is dash. A body accelerates uniformly from rest at 3 meters per second squared. Its velocity after traveling a distance of 24 meters is dash. So simple. How do we solve that question? Remember, I said before you can approach a motion problem, you must have three things. So let us try to see if we can get those three things from the question. Initially, I want you to note that the object was starting from rest. Starting from rest means that the initial velocity is 0. Please let us write that one down. We are also told that the acceleration is 3 meters per second squared. If the acceleration is 3 meters per second squared, we'll write that down to 3 meters per second squared. We are asked to find the velocity after traveling a distance of 24 meters. We have to find the velocity after traveling a distance of 24 meters. I want to find the velocity after traveling a distance of 24 meters. After traveling a distance of 24 meters. That should be very easy. Number one, how do I even know that the final velocity is the velocity they want me to find? Because I've been given the only other velocity that we have, that is the initial to be 0. So the other velocity, if they ask me to find any other velocity, it must be taken to be final. So I can now continue to solve the question. Here I've been given U, A, and S. I want to find V. So which of these equations has those 4 items? It clearly has to be the last equation, which is V squared is equal to U squared plus 2as. So if I sort out this, I will have V squared by substituting the values. U is 0 squared plus 2 multiplied by A3 multiplied by S24. So if we continue with the evaluation, V squared is equal to 0 squared is 0, 2 times 3 is 6, and 6 times 24 is 144. So our V squared is equal to 144. If we do V, we'll get the square root of 144. And the square root of 144 is 12 meters per second. So that is what I'm going to get. That should be the final velocity that the object will have with this acceleration after traveling that particular distance. So we'll move on to another question. Now, we are told, the next question goes thus. A car starting from rest moves with a uniform acceleration of 6 meters per second squared. What distance will it cover in the 4th second of its motion? A car starting from rest moves with a uniform acceleration of 6 meters per second squared. What distance will it cover in its 4th second of motion? Let us write out what we are given. We are given the initial velocity because we are told that the object is starting from rest, so the initial velocity must be equal to 0. If the initial velocity is 0, we are told that the acceleration is 6 meters per second squared. That means the acceleration is 6 meters per second squared. I can write that one down. We are now asked to find the distance that it will travel in its 4th second. Please, this is what I have been given, the fourth second of motion. Now, I need you to understand that the fourth second of motion is not the same as after 4 seconds. There are two ways by which time can be given. Time can be given after an exact number of seconds. For example, after 4 seconds, after 5 seconds, after 6 seconds. So in those cases, the question is very direct. You will just put those time for t. But time can also be given as a positional quantity in terms of position. Here it is given in terms of position. The distance traveled in the fourth second, it cannot be the same thing as the distance traveled after 4 seconds. How are we going to get the distance traveled in the fourth second? We need to really understand what is the fourth second. If I come to your class and I ask the best 4 students to stand up, how many students do you think will stand up? 4, right? The first person, the second, the third, the fourth will stand up. But if I come to your class to ask for the 4th place student, the 4th place student, how many students do you think will stand up? Only 1. Only the student that came 4th, probably in the last evaluation. So the 4th is not the same thing as 4. So the 4th second starts at the end of the 3rd second. There was a particular time that we can refer to as the first second. The first second is the time between 0 and 1 second. The second second is the time between 1 and 2 seconds. The 3rd second is the time between the 3rd and the 4th second. The second and the 3rd, sorry. The 4th second now is the time between the 3rd and the 4th. The 4th second started the moment the 3rd second ended, and it lasted through to the start of the 4th second. So if you want me to find the distance traveled within the 4th second, 0 seconds, 1 second, 2 seconds, 3 seconds, 4 seconds, I will find the distance traveled after 3 seconds. I will also find the distance traveled after 4 seconds. Then I will subtract the 2 of them from each other to get the distance traveled within the 4th second, which is here. So that is what the question wants me to find. So please always take note when they give you time in terms of positional quantity. 4th second, you must get the time after 3 seconds, just the time before the 4th, and the time after 4 seconds, then you subtract. Similarly, if I ask to find the distance traveled within the 9th second, you get the distance traveled after 8 seconds, just the moment before the 9th second, and the distance traveled after 9 seconds, then you subtract them. So what I will do here is I'm going to find the distance traveled after 3 seconds, after a time of 3. I will also find the distance traveled after a time of 4. Then I'll subtract the 2, and that should give me my answer. Now, if I want to do that, I will use the same quantity. In the first part, my u is 0, my a is 6, but my time is 3. I want to find the distance. In the second part, because I'm taking it from 0 again, my u will be 0, my a should be 6, and my time should be 4. So I want to find the distance. So once that is done, I can now subtract them. And the only equation that has these quantities is the third equation, x is equal to ut plus half at squared. So I will simply do s is equal to ut plus half at squared. My s is equal to, my u is 0, multiplied by t, 3, plus half times a. My a is 6, my t squared is 3 squared. So if I do that, x is equal to 0 plus 2 here 1, 2 here 3. So that becomes 3 times 3 squared. That should be 27. So my x must be equal to 27 meters. This is the distance traveled after 3 seconds. If that is the case, I will find the distance traveled after 4 seconds. So that becomes s is equal to u, still 0, t, 4, plus half times, what is my a, 6, multiplied by what is my time, 4 squared. So that should be s is equal to 0 plus 2 here 1, 2 here 3. 3 times 4 squared. 4 squared is 16. 3 times 4 squared is 48. 48. So the distance traveled after 4 seconds is 48 meters. The distance traveled within the 4th second must now be equal to The distance traveled after 4 seconds, 48 meters, minus distance traveled after 3 seconds, 27 meters, and that should clearly give us 21 meters. So that is how to solve questions that require you to find the distance within a positional time value. Now, we continue. There can be instances too now in physics when an object will move with these questions that we have solved and the equation that we have derived are for objects that moves with uniform acceleration, object that moves with uniform acceleration within the point where a particular velocity initial was established up till where another velocity, the final, was established. Now, there can be instances where an object within a question will move with more than one acceleration. There can be instances where an object will move with more than one acceleration. If that is the case, then you must break that question into the number of acceleration that it has. You must break that question into the number of acceleration that it has. If it has 2 accelerations, you must break the question into 2. You must break the problem into 2 and decide to solve it independently. You solve each part independently. If it has 3 accelerations, you must break the question into 3 different accelerations and you decide to solve them independently. The only link between each of those parts that you have now created is that where one stops, that is where the next part must begin. So therefore, the final velocity of one part must be the initial velocity of the other part. So one very good skill that you must now have in trying to solve problems like that is you must be able to read within the question to know the number of acceleration that that question has so that you will know the number of parts that you are going to break it down to. There are hints within the question. You can use the number of time values that is given. Where I've given you 3 different time values, then it is most likely a type of question that you have to break into 3 parts. But that time is not always the best thing for you to use because sometimes a time value they can choose not to give you a particular time value. So you need to read within the lines, how many acceleration do you think it has, and how many parts can we break that question into. We are going to solve a type of question like that so that you see how to treat those type of questions overall. Now, we are going to, I'll dictate the question, and we are going to try to see how to solve it. We are told that a body at rest is given an initial uniform acceleration of 8 meters per second squared for 30 seconds, after which the acceleration is reduced to 5 meters per second for the next 20 seconds. The body maintains the speed attained for 60 seconds, after which it is brought to rest in 20 seconds. We are asked to find the average speed of the object throughout the journey. What is the average speed of the object throughout the journey? What is the average speed of the object throughout the journey? What's the average speed of the object throughout the journey? I must mention here that anytime your velocity changes, there is an acceleration. I said it earlier. Now, when we say the velocity is changing, I hope you know that there are 2 different ways by which the velocity can change. It can change by increasing. It can also change by reducing. It can change by increasing. It can change by reducing. So if the velocity changes by increasing, that is more appropriately referred to as acceleration. When an object is accelerating, it is increasing its velocity with time. When an object is decelerating, it is reducing its velocity with time. So while an object can increase its velocity, it can also reduce it. When it is reducing it, we more appropriately refer to that as a deceleration or a retardation. An object can retardate, that means it is reducing its velocity. An object can decelerate, that means it is reducing its velocity. The retardation and deceleration can also be uniform, the way acceleration can be uniform. If an object is increasing its velocity by equal amount, it is moving with uniform acceleration. If an object is reducing its velocity by equal amount, then it is moving with uniform deceleration or uniform retardation. So when an object decelerates or retardates, we can still also refer to it as an acceleration, only that this time the acceleration is negative. So if you are told that an object is decelerating at 3 meters per second squared, because deceleration, retardation have the same unit as acceleration. If an object is decelerating at 3 meters per second squared, because there's no deceleration in my equation, when you check, there's no deceleration. What I have in my equation are acceleration values. So if an object is retardating and I still want to use the same equation for it, all I need to do is I will refer to them as an acceleration, but this time the acceleration is negative. A very good example, if an object starts with a velocity of 10 meters per second, and after 1 second, the velocity becomes 7 meters per second, then it becomes 4 meters per second. It means the velocity of the object is reducing. And once the velocity of an object is reducing, it clearly means that it is decelerating. So there are two ways I can refer to the motion of this object. I can say that the object is decelerating at 3 meters per second squared. If this is every single 1 second, if this happens every single 1 second interval. So if the object is decelerating at 3 meters per second squared, then its motion can be like this. If I'm going to refer to it as an acceleration, then I'll say it is accelerating at minus 3 meters per second squared. Minus 3 means if I subtract 3 from 10, I'll get 7. If I subtract 3 from 7, I'll get 4. So you can either say that it is decelerating at 3. By saying decelerating, you have already accounted for the reduction, or accelerating at minus 3. So if I'm going to treat deceleration as an acceleration, or if I'm going to use this equation to solve problems on deceleration, don't forget to always attach negative, because what we have is acceleration in the equation. So anytime, and there are instances where an object must decelerate. If you are going to park your car, then it means you must go from a state where the car was moving to a state where it is no longer going to move. It means you are going to slow down till it becomes zero. When you go to rest, when you come to rest, when an object is being brought to a stop, to a halt, the final velocity of that object must be equal to zero. And once the final velocity must be equal to zero, if you move from a point where your velocity was not zero to a point where your velocity becomes zero, it means you are decelerating. There is a deceleration in that question. Anytime your velocity reduces, there's a deceleration. Anytime your velocity becomes zero from a value where it was not zero, then it means you are also decelerating or retardating. Always take note of that. There are times I want to tell you that there's an acceleration in the question, but I won't use the word acceleration. I will say that the object comes from rest. For you to come from zero to a point that is not zero, you are going to change. You must change your velocity. And anytime you change your velocity by increasing it, it is acceleration. Anytime you are also told that the object comes to rest, it means there's a deceleration. You are reducing your velocity till it becomes zero. From a point where it was not zero, there's a deceleration, even if I did not mention it. So we can continue. I'll state the question again. A body at rest is given an initial uniform acceleration of 8 meters per second for 30 seconds, after which the acceleration is reduced to 5 meters per second for the next 20 seconds. The body maintains the speed attained for 60 seconds, after which it is brought to rest in 20 seconds. Determine the average speed of the body throughout the journey. Now, this is clearly an example of a problem that you have to break into parts before you can solve it. Why? There is more than one acceleration in the question. So it is not a question you will solve like a one true question. No, you have to break it into parts and you treat each part independently. And in doing so, please remember that I said the final of one must be the initial of the next. Now, we want to check the number of parts that we are going to break this into. I told you that you can sometimes look for the number of time values that is given. In this question, we are given 4 different time values: 30 seconds, 20 seconds, 60 seconds, and 20 seconds. You have that on your screen. So we have 4 different time values, suggesting that we might be breaking it into 4 parts. But like I said, time values, counting the number of time values to know the number of parts you are going to break the problem into is not always reliable. So sometimes we can use it, but it's not all the time that we can rely on it. because a time value can be intentionally removed from the question. But we need to know the number of acceleration that is there. That is the most reliable way of knowing the number of parts that are going to break a problem into. Let us look at it. A body is given an initial uniform acceleration, 8 meters per second. It has an acceleration of 8 meters per second initially. So that's the first part. It did that for 30 seconds, after which that same acceleration was reduced to 5 meters per second. The acceleration now became 5. The acceleration was 8 before. It now became 5. So we now have 2 accelerations. There was 8, acceleration of 8 that was used for like 30 seconds. Now we have 5 meters per second, still an acceleration anyway. The acceleration was 8, now it was reduced to 5. What is being reduced is not velocity. What is being reduced is acceleration. So we have an acceleration of 8 and we have an acceleration of 5. So we continue for the next 20 seconds. The body maintains the speed attained for 60 seconds. Remember that I told you at the start of the class that anytime an object maintains its speed, it also means that it's moving with uniform speed or uniform velocity or constant speed or constant velocity, steady speed, steady velocity. When your velocity is steady, not changing, uniform, and constant, it means that your acceleration is equal to 0. You are not accelerating during the period where you have decided to move with a constant velocity. And when the velocity is constant or the same, and you're not, it means the acceleration is equal to 0. So now let's take a record of the acceleration that we have had so far in the question. There was a particular time the acceleration was 8, then it became 5, then now it is 0. So we already have 3 different accelerations for the question. And we are now told that after which it is brought to rest, the object was moving, obviously, all through. Now it is suddenly brought to rest. It is brought to a point where it is not moving before. While it was going through all of its various accelerations, it will have velocity value, speed value, it was moving. When the acceleration was 8, when the acceleration was 5, when the acceleration was 0, it was the acceleration that was 0, not the velocity. It was moving with constant velocity. That means it has a velocity. The acceleration was 0 at that time, but the velocity is not 0. So at the end of that, it was now brought to rest. If it was brought to rest, it means there's a deceleration. That deceleration was not given in the question, but there's a deceleration. So if I have to break that question into parts, I'll break it into 4 parts. And those 4 parts are clearly highlighted by my explanation. I said it will have an acceleration of 8. It will also have an acceleration of 5. It will have an acceleration of 0. Then it will have a deceleration that is not stated. So I want to solve the question by breaking it into 4 parts. And how will I do that? The first part, the second part, the third part, and the fourth part. For each of these parts, I am going to try to solve the question. And I'm going to write out, for each of these first 4 parts, we are going to have initial velocity, the final velocity, the acceleration, the distance, and the time for each of these ones. So for the first part, we are told that the body was at rest and it was given an initial acceleration of 8 meters per second squared. The reason why they put the initial word for acceleration is there are still going to be other acceleration values for a time of 30 seconds. That's all for that first part. Because immediately after that 30 seconds, the second part started. They now said, after which the acceleration is reduced to 5. So for the second part, the acceleration is now 5. We're not given the initial velocity. The acceleration was reduced to 5 for the next 20 seconds. For the next 20 seconds. For the second part, that is all that we know. Because immediately after that 20 seconds, the third part started. The body maintains the speed attained for 60 seconds. For the third part now, the body maintains the speed, means the acceleration is equal to 0 in a time of 60 seconds. In a time of 60 seconds. And that's the end of the third part. They now said, after which it is brought to rest in 20 seconds. It is now brought to rest in 20 seconds. That means in the last part, it came to rest. Came to rest means the final velocity is 0 in a time of 20 seconds. That's all that we know. And this is a part that has the deceleration. This is a part that has the uniform velocity because the acceleration is 0. These two are acceleration values, only that the accelerations are different. In the first part, we have an acceleration of 8 meters per second squared. The second part, we have an acceleration of 5 meters per second squared. Sorry, I wrote that as meter per second earlier. So we can now solve for the average speed. Anytime you are asked to find the average speed, when we have a problem that has an acceleration or even multiple acceleration, I will write the average speed as the formula for average speed must be the total distance. You must find the total distance covered by the object, the total distance covered by the object over the whole of the journey, divided by the total time it took the object to cover that distance. So if I want you to find the average speed, I want you to also first determine the total distance across. Then you know the total time. Total time for this problem is not any issue because we have been given, we can easily find it. Here 30, here 20, here 60, here 20, we'll add them together. But I need to know the distance for the first part. What's the distance it covered in the second part, the distance it covered in the third part, and the distance it covered in the fourth part. So I am going to use that to solve the problem that we have. So another problem that I think I might have in this question in determining anything is I said you have to solve each part independently. The first part is not a problem because I know 3 things. I told you that before you can solve a motion problem, you need 3 things. I know those 3 things, U, A, T. I can easily find anything that I need in the first part. But when you check the second, the third, and the fourth, you will discover that we do not have up to 3 quantities. We are given for each only 2. A and T here, A and T here, and V and T there. So it looks as if we may not be able to solve for this and this and this. We are now going to solve this question by determining to make it up to 3 quantities here. Remember what I said, that where one stop, that is where the second will start from. So if I need to get one more quantity here for the second part, I have to go to the first part. I have to go and look at the final velocity that will represent where the first part will stop. It will automatically become the initial velocity where this will start. So the final velocity of the first part must be the initial velocity of the second part. Similarly, I will find the final velocity of the second part. It must also be the initial velocity of the third part. I will find the final velocity of the third part. It must also be the initial velocity of the fourth part. Once I can do that, I will see that I will have up to 3 quantities for each of those parts that I can now use to solve for the distance or the distance values. Now, so I can find the final velocity, though I don't need it for what I need to do, but I need it to be able to continue with others. So to find the final velocity here, I know U, A, and T. I can use the first equation. V is equal to U plus AT. So V is what I need to find is equal to my U, 0, plus my A, 8, plus my T, 30. So my V must be equal to 0 plus 240 meters per second. And my V must be 240 meters per second. And that is what I need here. So if my final velocity here is 240 meters per second, it means my initial velocity here will be 240 meters per second. So with these informations, I can also find V. So if I need to find V, V must be equal to U plus AT. My V is U, my U is 240 plus A is 5 multiplied by T, and T is 20. So we'll have 240 plus 100. 240 plus 100 will give us 340 meters as the final velocity of the second part.
So 340 meters per second being the final velocity of the second part must be the initial velocity of the third part, which is also going to be 340 meters per second. Here the acceleration is zero. Anytime the acceleration is zero, we observe that the final velocity and the initial velocity must be equal. So I don't even need to find it. It must be 340 meters per second because the acceleration is zero, u and v will be the same thing. So the final velocity of the third part being 340, it means the initial velocity of the fourth part will also be 340 meters per second. Now I want to determine the average speed. Don't forget the average speed formula. The formula for average speed is the formula for the average speed is the total distance all over the total time taken. The total distance divided by the total time taken. The total time taken. In doing so, I'll find the distance of the first part, I'll find the distance of the second part, I'll find the distance of the third part, I'll find the distance of the fourth part. Now, I even know 4 quantities, so I can easily find the distance from any equation that has distance. I can use S is equal to U plus V all over 2 multiplied by T. If that is the case, my U here is 0, my V is 240, I'll divide by 2 and I'll multiply it by my t. My t is 30. If I do that, I will have 240 divided by 2, 120. 120 times 30 is 3,600 meters. I'll do the same thing here too. Since I know it's u, I know it's v, I know it's t, I can find the distance. My distance must be equal to u here is 240, v is 340 multiplied by t is 20, and I will divide by 2. So S is equal to 240 plus 340 is 580. 580 divided by 2 is 290. 290 times 2 is 5,800 meters. Now I can continue with the distance of the third part. The distance of the third part must be equal to u plus v. U is 340. V is also 340. I'll divide that by 2 and multiply by 60. So 340 plus 340 should be 680. 680 divided by 2 should be 340. 340 times 60. 340 times 60. 340 times 60 should be 20,400. So 20,400 meters, while for the third part or the fourth part, my u is 340, my v is 0, I'll divide it by 2, still using this formula. The time is 20. I can say 2 year 1, 2 year 10. So the distance must be 340 plus 0, 340 times 10, that's 3,400 meters. So now that I know the distance for the first part, the second part, the third part, and the fourth part, I can find the total distance as 3,600 by adding all of them, plus 5,800, plus 20,400, plus 3,400. And I can divide through by the total time. The first part, I had a time of 30 seconds, plus the second part, I had a time of 20 seconds. The third part took a time of 60 seconds. The next part took a time of 20 seconds. So I can find the total distance by adding all of the values that I have. 33,200 meters is the total distance. The total time will be 30 plus 20, 50 plus 60, 110 plus 20, 130 seconds. So I'll divide my 33,200 by 130, divided by 130, and I have 255.38. 255.38 as the average speed for the whole journey. There are 2 different graphs that can be used to express the motion of an object. We can use the velocity time graph
We can also use the distance or the displacement time graph. The distance or the displacement time graph to represent the motion of an object. You can use either of the two to represent the motion of an object, depending on how the object moves. Now, these are the velocity time graph. Let's talk about the distance time graph. Distance time graph represents what the distance that the object is covering plotted against the time through which that object is covering that distance. So distance time graph represents the distance that the object is covering plotted against the time through which that object is covering those distance. And there are different instances, there are different type of shape that can be out that we can obtain from this graph. Number one, we can, if for example, the object is not moving at all, if an object is not moving at all, I want to represent the motion of that type of an object on a distance time graph. If an object is not moving at all, it means the object is not covering any distance. The object is not covering any distance. So at any time, the distance becomes 0. After 1 second is 0. After 2 seconds is 0. After 3 seconds is 0. After 4 seconds is 0. After 5 seconds, it is also 0. After 6 seconds is 0. So most of the time, when an object is not moving at all, we just draw it as an horizontal line on a distance time graph. Distance time graph. We just draw it as an horizontal line to show that the object is not moving at all. And that is it. There can be situations where the next set is the situation where the object is now moving, but is moving with constant velocity. If an object is moving with constant velocity, one thing I told you earlier is it will cover equal displacement in equal time values. If let us assume that an object is moving with a velocity of 10 meters per second, and at all times it is moving with that same velocity, it means that literally if I have to obtain the value of its distance at every point in time, after 1 second, I expect it to have covered a distance of 10. After 2 seconds, I expect it to have covered a distance of 20. After 3 seconds, I expect it to have covered a distance of 30. After 4 seconds, I expect it to have covered a distance of 40. After 5 seconds, it should have covered a distance of 50. If I decide to plot this, I haven't scaled my graph consistently, distance, time. If I decide to plot it, this is 1, 2, 3, 4, 5, 10, 20, 30, 40, 50. After 1 second, it has covered 10. After 2 seconds, it has covered 20. After 3 seconds, it has covered 30. After 4 seconds, it has covered 40. After 5 seconds, it has covered 50. If I join those points together, I will have a straight line that will pass through the origin. I will have a straight line that will pass through the origin. So therefore, anytime an object is moving with uniform velocity, if it is moving with uniform velocity, we expect the motion to be represented with a straight line that passes through the origin, something like that. So there can be instances where we will now be asked to find the velocity. Since it is moving with constant velocity, and that is why we have been able to draw it like this, we can be asked to find the velocity of that object. The motion of an object, once it is represented on a graph, we cannot use equation. There are two ways to solve a motion problem. You can either solve it with a graph or you solve it with equations. Once you are using graph, we don't want to see an equation. Usually what you want to do on a graph will either be like finding the area of that graph or finding the slope of the graph. Those are the two things that we normally do on a graph. When do we do slope and when do we do the area? When do we find the area? If a quantity in physics is obtained by multiplying two other quantities, if a quantity in physics can be obtained by multiplying two other quantities, and if those two other quantities are plotted against each other, either B against C or C against B, A, that is the product of B and C, will be found on this graph as the area. A, that is a product of B and C, will be found on this graph as the area. That means when you are multiplying, when you are finding area on a graph, you are finding a quantity that is equal to the product of what you have plotted on your y against what you have plotted on your x. A very good example is if we have a force distance graph. We are going to see that soon under work, energy, and power. If we have a force distance graph and they want us to find the work, we know already that work is actually force times distance, but we are not allowed to use formula when they are plotting graph. So what you will do that means the same thing as products on a graph is actually area. If I want to find work on a force distance graph, I will just find the area covered by the line, by the line on the graph. If I have a line, I will join that line to my x-axis, then I'll find the area of that line. I can even join it to my y-axis. It's not compulsory that it's a line. You can even have a quadrant. You can have a quadrant. You can have a quadrant of this form. You can have a quadrant of this form. Just know that if you want to find the work on a force distance graph, you will find the area. And it's not only work that you find with area on a force distance graph. Anytime, if you have a quantity in physics that is obtained by multiplying two quantities, such that those two quantities are now plotted on a graph, the quantity that you want to determine that represents their product is the area under the graph. Please put that to mind. Another procedure that is usually done on a graph is division. If there is a quantity in physics that is obtained by dividing two other quantities, division, now those two quantities are plotted against each other. Those two quantities are plotted against each other. Division in an equation is obtained by doing slope on the graph. Division in an equation is obtained by doing slope on the graph. Generally, this applies in physics. This applies even in mathematics and all other aspects that involve quantities that can be plotted on a graph. So when we have a very good example is I can be given a stress against strain graph under elasticity. We understand that Young's modulus is stress all over strain. Now that I have plotted stress against strain, then I can easily determine Young's modulus on the graph, not by using the formula, but by using the slope covered under the graph. Division means you find the slope. Multiplication means you find the area. Area and slope are two basic things that we do on the graph anytime we have them. So going back to what we have, if I have a distance time graph and I've been asked to find the velocity, I want to find the velocity or the speed. We already know that if an object is moving at constant velocity, the velocity is the distance all over time. Velocity is distance all over time. So now that I have a graph of distance against time, and I want to find the velocity, what I will just do is I will find the slope of that graph. And how will I get the slope? I'll just pick any 2 points, usually the start of the line and the end of the line. I'll call one point 1, the other point 2. That first point will have its own s. I'll call it S1. I'll get the s of the second point. If it's on the origin, the s is 0. I will also find the t of the first point. I'll call it T1. The t of the second point, I'll call it T2. I will now find the velocity by doing S1, by doing the change in s all over the change in time. And that will be S1 minus S2 all over T1 minus T2. And that is how I'm going to get the velocity anytime they present me with a graph of distance or displacement against time. That's how I'll get the velocity or the speed. The other form of motion that we can have is if the object is now accelerating. Anytime the object is accelerating, the speed is no longer constant. The speed is now changing. Because the speed is changing, The distance will also change, yes, but the distance will now not change in a linear form. It will not change in a linear form. Here it is changing linearly. The two of them are inversely proportional, they are directly proportional to each other. The distance and the time are increasing in a definite order. 10, 10, 10, 10, 1, 1, 1, 1. This is possible only when the object is having uniform velocity. And this is the graph for uniform velocity. But when the object is now having non-uniform velocity, when the object's velocity is non-uniform, it means that when the object's velocity is not uniform, it means that there is now an acceleration. And if there's an acceleration, the distance is not just going, the speed is not just going to be distance all over time. If there's an acceleration, this is what you have if there's no acceleration. If there's an acceleration, the relationship between speed and distance is s is equal to ut plus half at squared. Or the relationship between distance and time, is now this. Elsewhere, it was just s is equal to ut. This is a linear equation. This is an equation that if you draw it, you must get a straight line. This is an equation for a body that does not have an acceleration. If the acceleration is 0, if the acceleration becomes 0, this equation reduces to what we have here. And this is done. This is for objects that have the same velocity. But where there is where there's an acceleration now, it means that the relationship between distance and time is now quadratic. It is now quadratic. By the time you plot those type of equation, we should have a graph that looks like this. A graph that looks like a quadratic graph. This is the graph when there's an acceleration. This is the graph when there is no acceleration. And this is the graph where the object is not moving at all. The velocity is equal to 0. This is distance time graph when the velocity is 0. This is distance time graph when the acceleration is 0, the velocity is constant. And this is the distance time graph when the acceleration is greater, when there's an acceleration. So here, if you now want me to find the velocity, then I have to use, I said if you want to find the velocity, is the slope that you find. Here, if you want to find the velocity, you also find the slope, but you now have to find the slope because it is a curve. Finding the slope of a curve is not going to be so easy because a curve will not have a single slope. A line will have a single slope. Any 2 points that you pick on this line will give you the same slope. But a curve will not be like that. For the slope of a curve, then you have to be given the specific point that they want you to find the slope. I can ask you what is the velocity at time 3. Then you have to look for where the time is 3. You will trace it to the graph. You will draw a tangent to the graph. And that tangent is what you are going to use to find your slope. You put a straight line. A tangent is a straight line that touches the curve at only one point. So you will now find the slope of that tangent to get the velocity. Now we'll try to revise velocity time graph. For velocity time graph, we are also going to look at those 3 situations. When the object is at rest, for velocity time graph, when the object is at rest, it means that the velocity is not moving. It means the object is not moving, So the velocity is 0. Once the velocity is 0, that means no matter the time, you always meet the object at rest. When the velocity is 0, that is where you see it. It will be drawn with a line that is horizontal. When the object is moving with constant velocity, it simply means that the velocity of that object is constant. Let us assume that the body has a velocity of 20 and it was moving with that velocity for the whole of the length of the motion. It means that at any time, the velocity of the object will be found to be 20. So this is how we are going to draw it, considering the particular velocity that you are talking about. So when the object is moving with constant velocity, it is drawn with an horizontal line that meets the y-axis at the point where the velocity is indicated. So when the next thing is when the object is moving with a uniform acceleration, it's now accelerating, so the velocity is changing. If it is accelerating and the velocity is changing, how do we draw the velocity time graph of the motion of the object? The velocity time graph of the motion of the object will have to indicate that the velocity is changing, but the velocity is now changing by equal amounts in equal time interval. So that means if the velocity after 1 second, a very good example is the velocity after 1 second, 20, 30, 40, 50, 60. Velocity after 1 second, let's say is 10. The velocity after 2 seconds is 20. The velocity after 3 seconds is 30. The velocity after 4 seconds is 40. The velocity after 5 seconds is 50. The velocity after 6 seconds, let's say, is 60. So the velocity is increasing by equal amount in equal time interval. If I join it, I should have a straight line. I should have a straight line on the velocity time graph. So this is generally how we draw the motion of an object that is moving with uniform acceleration. If the object is moving with uniform deceleration, we'll show it that same way too, only that the shape of the graph will now be different. We are going to show deceleration in this case involves the fact that the velocity is reducing with time. If the velocity is reducing, let's say initially the velocity was 60. Then after 1 second, the velocity became 50. After 2 seconds, it became 40. After 3 seconds, it became 30. After 4 seconds, it became 20. After 5 seconds, it became 10. And after 6 seconds, it became 6. If we join that, this is how we show the velocity time graph of an object that is decelerating. So for a body that is moving with uniform acceleration, the velocity time graph is indicated with a straight line that is starting from the origin. That is, if it is starting from rest. It's possible that it's moving with uniform velocity, but it's not starting from rest. It's starting from a velocity that is not zero, and that is how we are going to indicate it. It is possible too that an object is moving uniform deceleration. If an object is moving with uniform deceleration, it means that from wherever it is starting, the velocity is going to reduce. So this is the line, the negative line is what we are going to use to represent deceleration. An object can decelerate to rest. Then we'll bring that deceleration line to a point where the velocity will be zero. It is possible too that the object does not decelerate to rest. It's decelerating uniformly from its velocity, but it did not come to rest. It came to a particular value of velocity that is not zero. So that is also true for that. Now the last part is how the velocity moving with non-uniform acceleration. If the velocity is moving with non-uniform acceleration, how do we draw the motion of that object? So the object can also move with non-uniform velocity. If the object is moving with non-uniform velocity, non-uniform acceleration, if the acceleration is not uniform, then we don't expect the velocity to increase by equal amount. The velocity is not going to increase by equal amount. It means the graph will not be a straight line graph. It can take any form from any type of curve that we have, depending on how the velocity is now changing. Depending on how the velocity is now changing, because the acceleration is not uniform, so the velocity is not increasing regularly, it's increasing irregularly. So if we plot it, we'll have different type of values, different types of graph that we can get from it. Now, we will try to take a question on non-uniform acceleration. We will try to take a question on velocity time graph, and we will end the topic. I will solve a question that has multiple acceleration. Before then, let me try to revise the velocity time graph particularly again. I can draw a velocity time graph like this. I can draw another the velocity time graph of a body like this. I can draw it like this. I can draw the velocity time graph like this. I can take any form, particularly when an acceleration is involved. So let me just interpret each one. Here it means that the object accelerated, then decelerated to rest. It accelerated from rest, then decelerated to rest. Here it means that from what we discussed earlier, the object moved with constant velocity for a while, then it accelerated, then it also decelerated to rest. Here it means the object accelerated from zero, from rest, decelerated, but it did not get to rest. If it had gotten to rest, then this is how we'll have represented it. So it did not get to rest. It stayed, it decelerated to a lower velocity than it started. Then it now continued to move with that velocity. Then it eventually now also decelerated to rest. So when you look at the straight lines, the usual form is that they take the acceleration, deceleration, or the constant velocity form. So and the three lines can now be combined in different manners. So we are going to take a question and we are going to try to see how we can solve problems using the velocity time graph. I will solve the same question that we solved earlier. The same question that we solved earlier using equation of motion. I want to solve it with the velocity time graph. We are told that a body at rest is given an initial uniform acceleration of 8 meters per second squared for 30 seconds, after which the acceleration is reduced to 5 meters per second for the next 20 seconds. The body maintains the speed attained for 60 seconds, after which it is brought to rest in 20 seconds. Draw the velocity time graph of the motion and use the graph to determine the average speed covered by the object. So to draw the velocity time graph, so what I will do now is to draw it. A body at rest is given an initial uniform acceleration of 8 meters per second squared for 30 seconds. The body is given an initial uniform, so there's an acceleration. There was an acceleration. I will indicate the velocity here after that acceleration period and the time it took it to get to that velocity. The time is 30 seconds, that has been given. We are also told that the acceleration is 8 meters per second squared. We cannot write the acceleration here. This axis is only for velocity. We can't write the acceleration here. This axis is only for time. So the only place that is available for us to write the velocity, to write the acceleration, is on the line, on the velocity time graph. So the body, after which the acceleration reduced to 5. The acceleration now reduced to 5. It is still an acceleration, but it is a lower acceleration than 8. So there are different forms of drawing lines that have acceleration. They are positively sloped. They are positive slope lines, so we can always just continue. So the acceleration here is 5 meters per second squared. So after accelerating, we expect that the final velocity, to have another final velocity, then it will have a time. We are told that it accelerated again for the next 20 seconds. For the next 20 seconds. The broken line that I'm using is to indicate what the velocity and the time values will be at the end of each acceleration values. So I can now continue. They now said the body maintains the speed attained for 60 seconds. Now, after getting to this speed, it maintained it for 60 seconds. It maintained the speed for 60 seconds. Mind you, the time must be cumulative. I must be adding the time. If from here to here is 30, from here to here will be 20. So the time that I will put here should be 50 seconds. 50, exactly 50 seconds. I will have to add the time. So it maintains the speed for 60 seconds. 60 seconds means this place will be 110 seconds. So now we are told that it is brought to rest in 20 seconds. It is now brought to rest in 20 seconds. Brought to rest in 20 seconds means it came down. In the next 20 seconds. So I will add the time to it. That is 130. So this is the velocity time graph of the motion of the object. It accelerated at 8, continued the acceleration not with 8 this time but with 5, then moved with constant velocity and came down to a velocity of 0. That means it decelerated. I told you that when an object decelerated, or when an object's velocity reduces to 0, it must decelerate. Now I want to find the total distance, the average speed covered, the average speed of the body throughout the journey, the average speed of the body throughout the journey. Mind you, I don't know. I now need to indicate the velocities at each point. After the first acceleration, it's starting with this velocity. Let me call it V1. That's the velocity at the rest position. V1 is obviously 0. It's getting to velocity V2, then velocity V3. So the first acceleration, it moves from velocity V1 to V2. The second acceleration, it moves from velocity V2 to V3. The third acceleration of 0, it stayed at velocity V3. Then when decelerating, it came from V3 back straight to V1. So that is the better way to represent this velocity time graph. Now I want to find this average speed. Average speed is total distance all over total time. So I must know the total distance. Distance on a velocity time graph is the area. On a velocity time graph, we find distance as the area. On a velocity time graph, the slope, acceleration, is the slope. Acceleration is the slope. So I can use this acceleration, knowing fully well that this acceleration has been obtained from the slope. I can use it to find V2. To do that, all I just need to do is I'll write the formula for the slope of this line. The slope, which is the acceleration, must be V2 minus V1 all over T2 minus T1. If I do that, my acceleration is 8. That has been given to me as a slope already. My V2, I don't know it, V2. My V1 is 0. My T2, this will be my point 2, because this is the point that gave me V2. Ultimately, it will also give me T2. My T2 is 30 minus my T1 should be here, and that T1 should be 0. So if I do that, I will have 8 is equal to V2 all over 30. My V2 clearly becomes 8 times 30. And 8 times 30 is 240 meters per second. 240 meters per second. So this is 240 meters per second. For the other part, I can also find acceleration. What is the acceleration? My acceleration is V3. This is the line. It is from, I can call this point 3, I can call this point 2. So point 3 is giving me my V3. Point 2 is giving me my V2. This becomes my T3. This becomes my T2. So I can do the acceleration. The acceleration of that line is given to be 5. What is my V? So the formula should be V3 minus V2 all over T3 minus T2. So that's 5 is equal to, my V3 is not given. My V2 is now known to be 240. My T3 is given to be 50. My T1 is given to be 30. That will be 5 is equal to V3 minus 240 all over 20. If I do that, V3 is equal to, V3 minus 240 is equal to 100. Clearly, my V3 should be equal to 340. So I've been able to find V2 as 240, and I've been able to find V3 as 340. And those are the only terms in this graph that I don't know the value of. So I can find the total distance. I find the total distance by finding the area of this graph, the area covered by this graph. Now, I can break it into shapes if I want to find the area, or if you know the formula that you can use to find the area of a mathematical shape that can be this represented, then you can also use it, but I'll break it into different shapes. The first one, I'll try to see if I can break it to a rectangle. It's always good to find the area with the x-axis. Find the area it's making with the x-axis. The next is a trapezium. This is a trapezium. I can find the area of this trapezium. The next is a rectangle. I can find the area of this rectangle. Then the next is a triangle. I can find the area of this triangle clearly. So if I do that, I should be able to get it. The area of this is the length times breadth, is half times base, times height. That is the area of the triangle. That should be half multiplied by, what is the base? 30. The base of this triangle is here represented on the x-axis, and it is 30. What is the height? The height of this triangle is 240. If we do that, we should have 2 here 1, 2 here 15. 240 times 15 should be 3,600. That was the exact distance that we got when we used the equation earlier. This is a trapezium. The area of this trapezium is half times a plus b times h. And that should be half multiplied by, what is a? Your a here is, if you have a trapezium, let me draw it out for you. It is the two parallel sides that will give you your A and your B. The height will not be the distance between the two of them. That's the height. So our A in this case should be, from here to here, which is represented on the y-axis as 240, plus our B in this case is from here to here, which is represented on this graph as 340. Then our height is the distance between the two parallel sides, and that is here, which is 20. If you do that, you will have 5,800 meters, which is exactly what we had earlier. Now this is a rectangle, very easy. The formula for finding the area of a rectangle is length times breadth. Our length is from here to here, which is 340. Our breadth is from here to here, which is 60. If we do that, we should have 20,400, 20,400. Then, for the other part, we are going to have this, and that is 110. That's half base times height, half times base. Our base is 20. And our height is 340. If we do that, 2 here 1, 2 here 10. The answer is 340 meters, 3,400 meters. So, to get the total distance, we'll just add this together. We'll add 3,600 plus 5,800 plus 20,400 plus 3,400. That is the total distance covered for this object. Then we'll just divide it by the total time, which is 130, and I believe we'll still get the same answer. So with that, we have come to the end of motion as a topic. I hope you've had a very interesting time. Thank you very much.